In this particular lecture, we are moving on to the shear stress in beams, its derivations, and the shear stress of various sections. So we have already seen the bending moment and shear forces. So what is the shear stress in a particular beam we will discuss today. Now uh, we are considering a beam, a loaded beam, a uniformly loaded beam, a cross section of a uniformly loaded beam. The depth, the width is dx, which we are considering is dx, and y is nothing but the distance from the neutral axis to the section we are taking, y. Okay, let m be the bending moment at AB. This at this point, the bending moment will vary along the section, right? The bending moment will change along the length of the beam. So at this point, let m be the bending moment. At this point, some additional bending moment may come for uniformly distributed load. So um, m plus dm be the bending moment at CD. Now the shear force at this particular section is F, and at this particular section, so at CD it is F plus dF. I is the moment of inertia of the section about the neutral axis. Now, as per the bending moment equation, m by I is equal to sigma by y. From that, sigma bending stress is equal to m by I into y, because this particular derivation is already given in lecture 20. Not lecture 20, no, lecture 18. Okay. Now, sigma is m by I into y for AB. At AB it is bending moment is m and I is the moment of inertia, y is the distance and all. So AB, at AB sigma is m by a into y. Now at CD, what is the bending moment? What is the bending stress? At CD the bending stress is sigma plus d sigma, because some additional stress may come. So sigma plus d sigma, which is equal to, instead of m we have to provide m plus dm divided by I into y. So there will be a change in bending stress as well as bending moment along the length of the beam, that is given here. Now the force acting across beam AB, the force acting across this point is, force is nothing but stress into area. So stress is sigma into area is A we are taking. So m by y into A is the total force acting at AB. Now along CD, what is the force? Again stress into area. Stress is nothing but sigma plus d sigma, that is m plus dm divided by I into y into area. Now the net, so these are the forces at these two sections. Now the net unbalanced force, what is the net unbalanced force? That net unbalanced force is nothing but, it is equation number 2 minus equation number 1. At section CD, what is the force, minus at section A, what is the force? That difference will give you the net unbalanced force, dm by I into y into A. That is the net unbalanced force. This force is known as shear force of the section. Now the total unbalanced force will, that is, we are just considering a small section from AB and CD, but the net unbalanced force, what is the net unbalanced force? The net unbalanced force is nothing but, it is from 0 to d by 2 we have to consider. Okay, so here the total depth is d, and this is a neutral axis, and this is d by 2, this is minus d by 2. So we have to consider the top portion above the neutral axis and below the neutral axis separately. So 0 to d by 2 you have to consider. So for getting the total force, what you have to do, you have to integrate the force which we got for a small section. So the force which we got for net unbalanced force we got for a small strip is dm by I into y into A. Now for the entire section, the total force will be integral 0 to d by 2. 0 is here and d by 2 is here. For the entire section is 0 to d by 2 into dm by I into A into y into dy. So while integrating, you will get it like this. dm by I is a constant. Integral 0 to d by 2 into ay dy you will get. So integrating area, you will get the total area as capital A. Integrating y, you will get the total y as y bar. Y bar is nothing but the distance between the center of gravity of the area and the neutral axis. So this is the neutral axis, and the area, the center of gravity of the area will lie somewhere here. So that is y bar. So while integrating, you will get it as dm by I into A into y bar. Got it? So this is the total unbalanced force above the neutral axis of this particular B. Below also there will be like the same. Okay, below also it will be like the same. The net unbalanced force below the neutral axis of the section will also be the same, because it is a uniform figure. Now the total shear stress. So the unbalanced force is nothing but, it is a shear force. Now the total shear force, the total shear stress is nothing but the total shear force divided by area. Total shear force we have got here. This is a shear force. The total shear force divided by area. Area of the section is nothing but B into dx, the cross sectional area. Cross sectional area is depth is the width is dx and depth is b. Dx into b at this point. So dx into b is the total area of cross section. So area will provide here, and we will find the total shear stress as dm by dx into ay bar into ib. Dm by dx is nothing but bending moment per unit distance. Bending moment by distance will give you force. Moment by distance will give you force. So tau is equal to force into ay bar ib you will get. This is the major equation to find the intensity of shear stress along the length of a B. Tau is equal to F into ay bar into ib. You have to know the derivation of this particular equation. F is nothing but the shear force. A is the total area of the section above the beam. Y bar is nothing but it is the distance between the neutral axis and the center of gravity of the figure. I is the moment of inertia about center of gravity, and B is the width. Got it? So this is the shear stress along the beam. Now we have to find the shear stress of so this is the general equation, tau is equal to F into ay bar ib. Now we have to find the shear stress distribution of different types of sections. For rectangular section, how will be the shear stress distribution? For that, what we are doing is, for all the sections what we are doing is, we'll find the area, we'll find y bar, and we'll substitute a and y bar in this particular equation. We'll find the tau. That's it for finding the shear stress distribution. For a particular rectangular section, we are seeing this as the rectangular section. We are taking a strip here. Okay, AJDK is a strip we are taking here. The width of the strip is B, and the strip is at a distance Y from the neutral axis of the section. Total depth is D. So this is our section we are taking. I is the moment of inertia of the whole section about its neutral axis. B is the width. AY bar is the moment of the shaded area. Now what we have to do is, we have to find the area. So what is the area of this particular section? We are going to find the shear stress distribution of a rectangular section. For that, we are taking a small strip. First, you have to find the area of the strip. What is the area of this particular strip? Area is length into breadth. Okay, here the length is B. What is the breadth? Breadth is nothing but total, it is this much distance is d by 2. Alle? Total is d, so half of that is d by 2. D by 2 minus y. So that is the width. D by 2 minus y is the width. So d by 2 minus y into b is the area of this particular section. Now what is y bar? Y bar is nothing. So in our equation A we got. Now y bar. Y bar is nothing but it is the distance between center of gravity of the section, neutral axis of the section and center of gravity of this particular section. We are taking this as the ഈ ഒരു സ്ട്രിപ്പാണ് നമ്മൾ എടുക്കുന്നത്. ആ സ്ട്രിപ്പിൻ്റെ സെൻട്രോയിഡ് തൊട്ട് ഈ സെക്ഷൻ്റെ neutral axis വരെയുള്ള distance ആണ് y bar എന്ന് പറയും. Y bar is nothing but it is the distance between, perpendicular distance between the neutral axis of the section and the center of gravity of the strip we are taking. So it will be at the center, right? For a rectangular section, the center of gravity is at the center, at some point here. So what is this point? It is y plus what is this particular distance? D by 2 minus y. This particular distance is d by 2 minus y. So half of d by 2 minus y. Y plus half of d by 2 minus y. This point you have to take. That is nothing but total d by 2 minus y divided by half is this particular distance plus y. Y plus d by 2 minus y into half. That is y bar. So you'll get it as y plus d by 4 minus y by 2. When simplifying, you will get it as half of y plus d by 2. So a and y bar you got. Now substituting the values of a and y bar in the previous equation, that is f is equal to a y bar ib, you will get it as f by 2i into d square by 4 minus y square. So this is the shear stress distribution, the equation for shear stress of a rectangular section. Got it? Now we have to find the shear stress distribution. Where is the maximum shear stress? Where is the minimum shear stress? That we have to find. So for that, where y is equal to d by 2, when we are providing y is equal to d by 2, y is equal to d by 2 means this particular point. Y is equal to d by 2 means this particular point. Y is equal to 0 means this particular point, that is neutral axis. So when y is equal to 0, what is the value? When y is equal to 0, the tau will be maximum. The shear stress will be maximum. When we are taking it as 0, we will get F by 2I into d square by 4. When y is equal to d by 2, we are providing instead of y, d by 2 we are providing, it will become d square by 4. So d square by 4 minus d square by 4 is 0. So the entire thing will become 0. So when y is equal to d by 2, tau is 0. When y is equal to 0, tau is maximum. And the shear stress distribution diagram will form a shape of a parabola. So at neutral axis, the value of tau is maximum, tau max, and at this point it is maximum, and this point it will be minimum. The same will be at the bottom portion also. Got it? So it will form the shape of a parabola having the maximum at the center, that is neutral axis, and having the minimum at the two extreme fibers. Got it? Now what is the maximum value? How to find the maximum value? At neutral axis, the value of tau is maximum. At neutral axis, what is the value of I? I for a rectangular section at neutral axis is b d cube by 12, and y is equal to 0. So substituting I is equal to b d cube by 12 and y is equal to 0 in the previous equation, in this particular equation you will get the maximum value of shear stress as 1.5 tau average. 1.5 tau average. Got it? You can substitute the equation and find how this particular thing comes. So tau max is nothing but it is 1.5 tau average. So this is the shear stress distribution of a rectangular beam. Got it? Now similarly we are finding it for triangular beam. The general equation is tau is equal to F into A y bar divided by IB. Now what is the uh, taking, so since it is a triangle, it is not a uniform figure, right? So you have to find the base of the triangle and all. So what we are doing is we are taking the triangle, we are finding a strip at the top portion AJK is the strip we are taking. The height of the strip we have taken it as x, let it be x. Okay, now the base is B and this total height is h. The beam, for the beam, base is B and total height is h. X is the height of the strip which we are taking. Now AJK and ABC are similar triangles. So JK by BC is equal to x by h. By using that, the width of the strip, that is JK, the value of JK is BX by h. So why we are finding this JK? Because we need that to find the area. So that's why we are finding this before itself. So Bx by h we got. Now the area of the shaded portion, that is AJK, area of this particular portion is half BH, right? Half into this altitude, this base into altitude. What is this base? Base we have found out as Bx by h. Into altitude is x. So half into Bx by h into x. Bx square by 2h is the area of this particular thing. Now what is y bar? Y bar is the distance between the neutral axis of this particular rectangle to the neutral axis of this strip, to the centroid of this strip. What is the center of gravity of the center of gravity of this triangle? Neutral axis of this triangle is nothing but it will lies at 2h by 3 from the top, h by 3 from the bottom. H by 3 from the bottom means 2h by 3 from the top. So at some point here it will be the neutral axis of the strip. So that is 2h by 3 at the point 2h by 3 from A. Got it? So this is 2h by 3. Now from this point to the neutral axis or the centroid of this triangle will give you y bar. The distance between this point to this point will give you y bar. Now what is this distance? The total height is x. So the centroid of the triangle will be lying at a distance 2h by 3 from the vertex. 2h by 3 from A. 2h by 3. Instead of h, here x will be there. So 2x by 3 from A. So the total y bar will be from this point to this point, it is 2h by 3 minus 2x by 3. You will get it as 2 by 3 into h minus x. So A and y bar you got. You have to substitute that in equation, and A y bar you got. What is B? B is the base of the strip we are taking. Base of the strip is BH by x. For the case of a rectangle, it was B itself. Why? Because it was an entire uniform length. Here also it is B, here also it is B. In case of rectangle, here also it is B, here also it is B. But for triangle it changes. Here it is B, but for our strip which we are considering, the B is nothing but it is BH by x. BX by h. So B also we have substituted. The value of B, instead of B we are providing Bx by h. Instead of A we are providing Bx square by 2h. Instead of y bar we are providing 2 by 3 into h minus x. You will get the value as f by 3I into hx minus x square, tau. Okay. Now for getting the maximum value, we don't know where will be the maximum value. So what we are doing, the maximum value of stress will be at a point where the differentiation of this particular tau, that is d tau by dx is equal to 0. The maximum value of tau will occur at a point when d tau by dx is equal to 0. Tau you know, tau is this one. So d tau by dx is equal to 0. If you are substituting it, the position of maximum value, the position of maximum shear stress we will get. So for finding the position of maximum shear stress, we are substituting the derivative of tau to 0. So that means f by 3I into d by dx of hx minus x square is equal to 0. F by 3I, we cannot substitute it to 0, so it will come here and it will become 0. So hx minus x square is equal to 0. So h, when we are differentiating this one, h minus 2x is equal to 0. That means x is equal to h by 2. That is, the maximum shear stress occurs at a point h by 2 from A. H by 2 from A. At that point, the maximum shear stress occurs. The diagram will be a parabolic diagram. At this point and this point, it will be 0. The maximum shear stress will occur at a point h by 2 from the top portion of the triangle. Now, for finding the value, we know this is the maximum point, maximum shear stress point. What is the value of the maximum shear stress? For that, what we have to do, instead of x, we have to provide h by 2 in the previous equation. So this is equation. In this equation, instead of x, we have to provide h by 2 for getting the value of maximum shear stress. Maximum shear stress we got as 1.5 toe average. The maximum shear stress is 1.5 toe average. When we are providing x is equal to 0, we will get the minimum shear stress, that is 0. Got it? So this is the shear stress distribution diagram for a rectangular beam or triangular beam. Now for a circular beam, if the beam is circular in shape, then what will be the shear stress distribution diagram? General equation is F into A y bar divided by IB, and we are considering a small strip at this point. Now what is this JK? JK is the chord of the circle. Okay, we have to find JK, right? JK is nothing but it is a chord of this particular circle. So the chord of this particular circle, the equation for chord is 2 into root of r square minus y square. So that you can take chord length of a circle is directly taken. Now area of the shaded portion is nothing but A is equal to 2 into root of r square minus y square into dy. Why? Because this is nothing but the area of a sector of a circle. Area of a sector of a circle. This portion is known as a sector of a circle. So this is also a direct equation. In your mathematics, you may have studied this, 2 into r square minus y square into dy. Dy is nothing but it is this height. So that also you got. Now the moment of this area is this one. The moment of this area is nothing but the area into perpendicular distance. Perpendicular distance is y. Okay. Now the moment of the area is nothing but a y bar. A into y is the moment. Area into perpendicular distance means moment of the area. Now moment of the whole shaded area. For the total shaded portion, what is the moment of the area? That is a y bar. A y bar is equal to integral. From where to where you have to integrate? From y to r. This is y and this is r. So y to r, the total moment of the area is equal to integral 2y r square, 2 root of r square y, where nothing but it is b, and y dy. 2 root of r square y square is a b. Y is directly taken down, dy is also directly taken down. So you will get a y bar is equal to integral y to r b y dy. Got it? Now width of the strip b is 2 into root of r square. B square is nothing but it is 4 into square of this one, 4 into root of r square minus y square. We have already seen that things. Now differentiating this b square, you will get 2b. Differentiating this b square in both ends, you will get 2b into db is equal to 4 into minus 2y dy. So while differentiating, you have to open this bracket to form r square minus y square, the whole raised to 1 by 2 you can take. Okay, then differentiating, you will get 4 into minus 2y into dy is equal to minus 8y dy. So y dy, from this equation you can rearrange this equation and find y dy is equal to minus 1 by y b db, minus 1 by 4 b db. So here you got y dy. Instead of y dy, what we are going to do is, here you have given the integral from y to r b. So y dy have to be converted in terms of b db. That's why we are doing this particular step. And y dy is nothing but minus 1 by 4 b db. So this value we have put here. So minus 1 by 4 b db. So you'll get minus 1 by 4 is a constant. We are taking outside, integral y to r b square db you got. Now when we are taking b as a component, b as the differentiating component, you have to change the limits. We have already provided the limits y and r for y. Okay, ഒരു വെർട്ടിക്കൽ ഡിസ്റ്റൻസിനുള്ള ലിമിറ്റ് ആണ് നമ്മളിവിടെ പ്രൊവൈഡ് ചെയ്തിരുന്നത്. നമ്മളിവിടെ ലിമിറ്റുകളൊക്കെ മാറ്റി നമ്മൾ എന്ത് ചെയ്തു, നമ്മളിതിൻ്റെ ഡിഫറൻസിയേഷനെ ബി കൊണ്ടാക്കി. അപ്പോൾ ബിയുടെ ലിമിറ്റ് പ്രൊവൈഡ് ചെയ്യണം. അതായത് y എന്ന് പറയുന്നത് y ആണെങ്കിൽ, y is when vertical distance is y, at this point what is the value of b? b is equal to b. Base is b. Okay, this point is b. Now when y is equal to r, y is equal to r എന്ന് പറയുന്ന പോയിന്റ് ഏതാണ്? ഈ പോയിന്റ് ആണ്. y r ആണെങ്കിൽ b യുടെ വാല്യൂ എന്താണ്? 0. When y is equal to y, b is equal to b. When y is equal to r, b is equal to 0. So instead of this particular limits, we have to provide this 0 and b. That is a y bar is equal to minus 1 by 4 b to 0 b square db. Okay, or 1 by 4, and so this limits can be reversed by multiplying it with minus 1. So 1 by 4 into integral 0 to b square db you will get, eliminating negative sign. So you'll get it as finally b cube divided by 12. A y bar is equal to b cube divided by 12. What we are doing is we have to find the shear stress diagram for a circular section. For that a y bar we have to find out. A y bar is nothing but it is b cube by 12 for a circular section. So in our general equation, that is f into a y bar divided by ib, we are providing this value of a y bar, that is b cube divided by 12, and you will get the final answer as f into r square minus y square divided by 3i. Instead of b, we are providing 2 into root of r square minus y square. Substituting that and you will finally get this equation. So that means tau increases as y decreases. From this equation it is clear that as tau increases, y will decrease. Now you have to find the shear stress distribution. So when y is equal to r, tau is equal to 0. Y is equal to r means at this point tau is equal to 0. At downward portion also, we are always considering half portion. For the other half it will be same. So at y is equal to 0 it will be 0. At this point also it will be 0. Now where will be maximum? When y is equal to r, tau will be 0. When y is equal to 0, tau will be maximum. So it will form a parabolic curve, and we have to find the maximum value of maximum stress by providing y is equal to, instead of y we have to provide 0. Maximum stress will be at the point y is equal to 0. So instead of y in the previous equation you have to provide 0, and at that point I will be pi d raised to 4 divided by 64, because the moment of inertia of the circle through its center of gravity will be pi d raised to 4 by 64. So providing that, you will get 1.33 tau average. That is the maximum value of shear stress, and this is the shear stress distribution diagram for a circular section. Now the distribution of shear stress over an I section is given here. This is also an important thing, as the same as earlier rectangle and all. So the general equation is f into a y bar ib. Now we have to consider two important cases here when y is greater than d by 2. So here you can see this is an I section. The breadth of this flange is web is b, and the flange is capital B. Width of or depth of this flange is web is d, and total depth is capital D. Since this is d, half of this is d by 2 and d by 2. The neutral axis lies at this is a symmetrical figure. So the neutral axis lies at its center, and d by 2 and d by 2. Capital D by 2 and small d by 2. You will get it like this. Now you have to consider two cases here. When y is greater than d by 2, that is when y lies at this flange. Okay. When y is less than d by 2, that is when y lies in this web. So two cases you have to consider. Y is taken from this point to somewhere here, or here, somewhere along this line. So y can be greater than d by 2 or less than d by 2. So first we are considering the case in which y is greater than d by 2. That means y lies in the flange. Okay, so we are considering a section here, section having breadth b, and the distance from the neutral axis to that particular section is y. So area of the section, what is the area of the section? Area is nothing but it is capital B into this width. What is this width? The total distance is d by 2. From this 0, the total depth is d by 2 minus y. D by 2 minus y is the total width into breadth. B into D by 2 minus y. That is the area. Now what is y bar? Y bar is nothing but from this point to the center of this one. What is the distance? So what is so you have to consider this, up to this it is y plus the center of this one. Center of this one means d by 2 minus y by 2, center of this point. So d by 2 minus y the whole by 2 plus y is y bar. So y bar and a you got. So instead of this in our general equation, this is the general equation, right? So a and y bar you got. You are providing the value of a and y bar here. And you will get the final answer as f by 2i into d square by 4 minus y square. So when y is equal to d by 2, shear stress is 0. At y is equal to small d by 2, the shear stress will be, so you have to consider when the y is within this, we are considering y greater than d by 2, that is y may lie at this point or within this point and this point. So the maximum and minimum value of y you have to find here. Maximum value occurs when y is equal to d by 2, small d by 2, and minimum value occurs when y is equal to capital D by 2. That two values you have to find. Okay. Now when y is less than d by 2 means y lies somewhere within the web from this point to this point. So we are considering a section. You have to consider a section accommodating this two. Okay. Now what is the area of this particular section? Area of the section is nothing but it is this area. Area of this rectangle plus this small rectangle. What is the area of this particular rectangle? That is b plus d by 2 minus d by 2. Capital D by 2 minus small d by 2. That is the area of this rectangle. Plus, what is the area of this rectangle? D by 2 minus y. Okay, capital D by 2 minus small d by 2. What is the area of this particular rectangle? That is d by 2 plus half of d by 2 minus d by 2. Got it? So that is the total area of this particular. So both the rectangle you have to found and the total area you have to find. Okay. Now the total area you got. Now what is y bar? Y bar also you have to find like that. Y bar of this particular rectangle plus y bar of this particular rectangle. Y bar of this particular rectangle is nothing but this distance plus half of this distance. Y bar of this particular rectangle is this distance plus half of this distance. So that will give you total y bar. So total a y bar you have to find. Got it? Now that a y bar you have to substitute in this particular equation for getting the value of tau in when it is less than d by 2. Got it? Now the maximum shear stress at that point also you have to find. Now you will get the shear force diagram for this particular section as this. Like this it will get. Here it will be constant, and in the web when it is within d by 2 you will get it like this, and when it is within this one the maximum value will be at d by 2 and the minimum value at this point. And at the web portion, at the beginning, the joining point between the web and flange, it will be a constant somewhat. At this point also it will be, here it will be this value itself, and here it will be maximum. So the shear stress distribution diagram for an I section will be like this. Okay, so this is about the distribution of shear stress over a beam section. Thank you.